AI is everywhere, right? It's making all these decisions that affect our daily lives. But here's the kicker. A lot of the time, we have absolutely no idea how it's making those decisions. So today, we're going to crack open that black box with a new method called SYMPOL. And what we find inside could totally change how we think about the future of AI. And that really brings us to the core question here. I mean, if an AI is driving a car or helping a doctor with a diagnosis, but it can't explain why it's doing what it's doing, can we really put our trust in it? It's one of the single biggest hurdles facing artificial intelligence today. So before we can really appreciate the solution, we first have to get our heads around the problem itself. It's what everyone in the field calls the black box problem, and it's a huge issue in one of the most powerful ways we train AI. And that type of training is called reinforcement learning, or just RL for short. The easiest way to think about it is like training a puppy. The AI or the agent tries a bunch of stuff, it gets a reward when it does something right, and over time, through trial and error, it learns how to hit a goal. And it works. I mean, it works incredibly well, but it has a dark side. Hey, don't just take my word for it. The very researchers behind SYMPOL put it perfectly. The policies, which are just the rules the AI learns, are often a complete and utter mystery. They're all tangled up inside a complex neural network, which makes trying to understand them basically impossible. And that's just not going to fly in situations where lives are on the line, like with self-driving cars or robotics. So here's the breakdown. On one hand, you have your typical black box AI. Think of it like a giant, tangled ball of yarn. You have no idea how it's all connected. On the other hand, you have what we want, an interpretable AI, like a simple decision tree. It's just a flowchart, a clean set of if this, then that rules. You can follow its logic step by step. It's predictable, it's explainable, and it's something we can actually trust. Okay, so you're probably wondering, well, if the decision tree is so great, why don't we just use that from the start? That's a great question, and researchers have been trying for years, but the old way of doing things had this one massive, critical flaw. So the old method is called distillation. Here's how it worked. First, you train your super powerful, super complicated black box AI. Then you try to distill all that knowledge into a simpler model, like a decision tree, by basically telling the tree to copy the big AI. But, and this is the big but, the copy is never perfect. You always lose critical information in that translation. And this creates what the paper calls a mismatch. What you end up with are two totally different AIs, the powerful one that actually learned the task, and this simpler, less accurate one that you're looking at. So you're not really understanding the original's logic, you're just looking at a blurry, incomplete photocopy of it. All right, so this is where SYMPOL comes in and just flips the whole script. It throws that entire flawed distillation process right out the window and comes at the problem from a completely different angle. The absolute genius of SYMPOL is that it doesn't bother making a black box in the first place. Instead of training a complex AI and then trying to simplify it later, SYMPOL learns that simple, easy-to-read decision tree directly, right from the get-go. It's all one clean process, no translation necessary. And this is a huge deal. It means no more post-processing and, crucially, no more mismatch. The policy the AI learns is the policy you can read and understand. What you see is literally what you get. And, as a bonus, it's designed to plug right into the popular AI frameworks that researchers are already using. It's a real game changer. Okay, that all sounds fantastic on paper. But you know the drill. Does it actually work in practice? We've got to see the receipts, so let's look at the data and see how SYMPOL really stacks up. First off, simplicity. The decision trees that SYMPOL creates are tiny. On average, they have just about 50 nodes or decision points. Now, to put that into perspective, the old methods would often spit out these massive trees with hundreds of nodes. At that point, you're pretty much just trading one black box for another. But here it is, the moment of truth. Information loss. This table uses a stat called Cohen's d to measure that mismatch. All you really need to know is that a big negative number is very, very bad. It means there's a huge gap between the real AI and the simple copy. And look at the numbers for the other methods. They're massive. Now look at SYMPOL, negative 0.019. That is so close to zero, it's considered negligible. The copy is practically a perfect match. And wow, this chart just says it all, doesn't it? That giant bar, that's the information gap for the other methods. And SYMPOL, it's that tiny little sliver down at the bottom that you can barely even see. This is the proof in the pudding. SYMPOL closes the gap. So we've seen the numbers, but why does this matter so much? Why is this mismatched thing so dangerous in the real world? Well, the paper gives this perfect, almost scary case study that shows how a black box can look like it's doing everything right while secretly hiding a huge flaw. So here's the setup. It's a simple little world. There's an AI agent, and its job is to get to the green goal square. The one big rule: don't touch the lava. Seems easy enough. So they train a standard black box AI on this. And it's a star student. It solves the puzzle perfectly. 100% success rate. So you'd think, great, job done, let's move on. But remember, because it's a black box, we can see what it did, but we have no clue why it succeeded. But then they use SYMPO, and it lets them peer right inside the AI's brain, and what they find is shocking. The agent never learned to find the green goal. Nope. It learned a much simpler, much dumber rule. Basically, keep the wall on my left and just keep walking. It was just a wall follower that got lucky. And that's the whole problem right there. We, the human designers, intended for it to learn this complex goal of finding the green square. But what it actually learned was a cheap shortcut: just hug the left wall. Now, in this one specific level layout, that trick just happened to work. But what happens if we change the level? You guessed it. The moment you move the goal or change the lava pits, the agent is completely lost. It just keeps trying to follow the wall because it never actually understood its real mission. This kind of failure has a name: goal misgeneralization. And inside a black box, this flaw is totally invisible until something goes wrong. SYMPOL makes it obvious from the start. And this isn't just about little agents in a game, of course. This ability to see inside an AI's mind has massive, massive implications for building AI systems that we can actually trust with really important jobs. This is where it all hits home. We need to know that a self-driving car stops at a red light because it understands the rule, not because it learned a shortcut, like just stop when the car ahead stops. A doctor using an AI needs to be able to ask why it's suggesting a diagnosis and get a clear answer. On our roads, in our hospitals, in our factories, being able to understand an AI's logic isn't a nice-to-have feature. It's the absolute foundation of safety and trust. Which really leaves us with this one final thought to chew on. As AI gets more and more powerful and we weave it deeper into the fabric of our society, methods like SYMPOL that pry open that black box become essential. Because ultimately, you have to ask, if we can't understand what an AI is thinking, can we ever really be sure that we're the ones in control?